Hey Calc. Um, if you're watching this, that means we've kind of extended out a little further than I was originally thinking, or we didn't take time off for registration and things, which I was planning on having this, or you didn't take the AP test, which is possible because it would collide up in if none of you decided to take the AP test. So I'm going to push us out into chapter 11 a little bit, and I'm going to have lessons posted for 11.1 and 11.2, I think, and then I'll probably wrap any videos that I make for this. It's possible that you're seeing this, and it's possible that you're not, but it is possible I'm using this years later. So I'm coming from my basement yet again to talk about infinite series. So first off, I want to talk about what infinite series is. So a sequence is a number pattern, and a series is the sum of all values in a sequence. So if we're talking about series, a series is the sum of all values in a number pattern. Now, most series have a start point and an end point, and we worked with these back in Algebra 2. However, back in Algebra 2, we also talked about the fact that there are some series that work infinitely, and the only way a series would work infinitely is if it's shrinking as it builds toward a certain point. So if all the way out at infinity we had a set value for our series, then for our sequence, then our series could be infinitely added up. And more specifically, the only way it'll work is if our sequence's set value at infinity is 0. So if the sequence is headed towards 0, ultimately, then the series can be summed throughout the whole thing. And I used a water bucket example back when I taught about this, but I'll talk about it again quick. Let's just pretend that I have a bucket, an empty bucket, and I fill half of the bucket with water, exactly half. Well, then I take and I fill half of the remaining half with water. And then I fill half of the remaining half with water. And then I fill half of the remaining half with water. And eventually I'm just putting like little drips of water into this bucket, and the bucket gets half more full each time, but it never actually fills all the way because the amount of water that I'm adding each time is becoming significantly smaller. So eventually I'm basically adding no water at all, and the bucket will never reach its peak. The same has to be true for these series that we're talking about. In order for us to calculate series infinitely, the values that we're adding each time have to be shrinking to the point where they've almost completely disappeared, so that we're not adding to the bucket anymore. Now, today's lesson is going to be broken across a couple different things. First, we're going to talk about how to take a pattern and write a series. Secondly, we're going to be talking about how to take a series and calculate its value over a set chunk. And then we're going to talk about how to decide whether a series is convergent or divergent. Will we be able to find the series over every value or not? Now, we won't be doing any actual finding the series all the way to infinities, but we're preparing to be able to do so. we're preparing ourselves to see if a series can be found all the way to infinity. But in order to do that, we have to be able to look at the series, the values, and create a formula, and we have to be able to look at a formula and understand what the values say. So that's our first job here. So I'm going to come in and focus on what I've drawn over here, which is a sigma notation for any given series. So sigma notation simply says the series of all values in this function from 1 all the way to infinity. So basically you're going to put all the numbers into this function, whatever this function might be, from 1 to infinity, and then you'll add them all up, and you're going to get the series here. So this is our start, that's our end, and this is our equation. Now we're going to move forward and look at creating equations. Now, equations are built numerator and denominator separately. So when I look at an equation like this, I'm going to look at the numerator separately from the denominator and build my equation based on what I'm seeing. And some of these are going to be really easy to see, and some of them are more complex to see. Most of the ones you're going to work with today are going to be pretty easy to see, but they can get a bit more complex. So this is problem 1 from our homework, and that's where I'm going to use as my jumping off point. The homework is on page 618, 1 through 10, 19 through 24, if you're following along in the book with me. All right, so if we look at the numerator, just the numerator of this, you'll notice that the numerator on this problem is always 1. Therefore, the numerator in our equation will just be 1. It's not a moving target. It's not something that we need to formulate. It's just a constant, and it's 1. So we can go ahead and make the numerator 1. You'll notice down here on problem 5, that is not the case. But up here in problem 1, the numerator is just 1. Now the denominator is a different thing altogether here. So we have to figure out our denominator pattern in order to move forward on creating this equation. So I have 3, 9, 27, 81. So this is a times 3 pattern that we have flowing through here. Now the key to this is to lock down our starting value as part of our formula. Now I'm using x in my scenarios here. The book's often going to use n. So if you want to use n instead of x, that's fine. So I'm going to say that's 3x sitting in the bottom, because in the first term x will be 1, and 3 times 1 is 3. In the second term x will be 2. Oh, 2 times 3 is not 9. Oh, so my times 3 didn't work. Oh, okay. So this is not a times equation, is it? It's actually a power equation. When I want a times pattern, like the one that I was looking for there, and that's what I wanted, was a times pattern, I can't use a times equation. The times equation got me an addition pattern. So I had 3, and then I had 6, and if I would have continued, I would have had 9, and that's not the pattern that I'm seeing here. That would be an arithmetic growth pattern, not a geometric growth pattern. The key to getting the times pattern is powers. 3 to the x power. Now let's look at my equation. 3 to the x is 3 to the first would be 3. 3 to the second would be 9. 3 to the third would be 27. 3 to the fourth would be 81. So when I'm looking at that multiplying pattern, I'm going to use an exponent to create that. That's my function that I'm looking for. Now let's jump down here to this problem. because this problem gives us a couple of new elements that we need to deal with. We can start with our sigma, x equals 1 to infinity. The first thing you'll notice on this problem versus the previous one is this rotational negative. So that immediately tells me that I need to do -1 to a power as part of my function. And the key here is, are they the odd ones? Is it 1 and 3 and 5 that are negative? In this case it's not. Or the even ones that I'm looking at that are negative. If the even powered values are negative, I'm going to put n minus 1 up top so that it shifts my power. If the odd values are negative, I'm just going to use n. So when you're doing this positive negative rotation, if it's the odd values that are negative, 1, 3, 5, then you just want n as your power. If your even values are negative, then you want n minus 1 as your power. Now let's kick into what the actual pattern is. This takes care of my positive, negative, positive, negative, positive, negative. On the top, I have an interesting pattern. These are all perfect squares. So instead of being a timesing pattern and having a power like this, I still have a power situation, but in this case, the power is squared, and the base of my situation is my n value. So I have 1 squared for my first term, which is 1, and I have 2 squared for my second term, which is 4, and I have 3 squared for my third term, which is 9, and I have 4 squared for my fourth term, which is 16. X squared is the equation that gets me the top values there. Now the bottom values are slightly different. They're growing by 1 each time. This is not a constant like it was up here, but it's not much different than it was up here. Over here I have 2 and then 3 and then 4, so I'm getting this +1 pattern each time. Now to get the +1 pattern, I do 1 times whatever my value is. So but if I leave this as my answer, 1x, I would have 1, 2, 3, 4, 5 as my values down below. So I need to adjust them slightly because I didn't start with 1 here. If it went 1, 2, 3, 4, I would be good right now. But because it starts at 2, I need to add this 1 over here. If it started at, say, 5, I would add 4, because typically my pattern would start at 1. Now, if my pattern is +2, it would be 2x plus whatever shift that I needed to make. If it was, if it was 5 and then like 15 and then 45, I would need 3x, and then I have to shift +5 because or +2 because I started over at 5. So I mean, you can see that all of these different possibilities are possible. You just have to figure out the formula that fits with those pieces. So that's going to get you through problems 1 through 6. Now problems 7, 8, 9, and 10 ask you to find the sum of the series through the 4th term, which is actually the easiest part of the homework, but I'm going to walk through one of them, and that's problem number 8. So problem number 8 gives us the formula, the series from 1 to infinity of n over n plus 1. And I just want the first 4. So term number 1 is what I get when I put in 1 here. So I have 1 over 1 plus 1, which is 1/2. And then term number 2, I put in 2 here. So I have 2 over 2 plus 1, so 2/3. And then I put in 3 here, and I have 3 over 3 plus 1, which would be 3/4. and then I'd have 4/5, etc. Now I only need the first 4 added together, so I'm going to do 1/2 plus 2/3 plus 3/4 plus 4/5. So 1/2 plus 2/3 plus 3/4 plus 4/5, and that gives me 2 and 43/60. Now the pattern here comes from that formula, and that's an interesting formula, and this is actually the same formula we were using in the last one, 2, 3, 4, 5, 1n plus 1 because it's shifted over, but the top is just 1n because I do plus 1 each time. So I just wanted to rotate that back and point that out for all of you. So now we need to really talk about the meat and potatoes of the lesson, which is convergence versus divergence. So this piece of this is the most important piece of what we're really trying to get at here in 11.1 to set you up for the next couple of sections. All right, so a function will converge if it is headed toward, if the limit of the sequence is headed towards 0. So if your sequence is headed toward 0, then your series will converge. Now you're going to find this concept very similar to L'Hopital's rule and what we were talking about with convergence and divergence with L'Hopital's rule. But the key difference between what we're talking about now and when we were talking about L'Hopital's rule is with L'Hopital's rule, we were talking about the integral of this thing being convergent or divergent. Right now we're talking about the actual function being convergent or divergent. So the key is still the harmonic equation, which the harmonic equation is 1 over x or 1 over n. This is still our anchor, it's still our key. And the rule with L'Hopital's rule is you had to have a bigger power than 1 difference in the denominator, right? So the denominator had to be 1 full power bigger than the numerator in order to swing that power far enough so that this would in fact converge. With infinite series, we don't need quite that much power. It doesn't have to be a full power larger in the denominator in order to push it all the way over. The denominator's power has to be greater than the numerator's power, at least by 1. And then the denominator has to have at least a plus 1 push above that. So right now, this is too small to converge. This diverges. However, 1 over x plus 1 converges. This tiny little plus 1 swing pulls this function far enough that we would say its series will converge. This series will diverge. This series pulls far enough that it will converge. So it has to be a full power plus at least a little something. Now, if the denominator is a power bigger than the numerator, that converges, and that's not a problem at all. But if we're kind of on the fence and hanging out here, this is convergent, that is divergent. So something like this, if I had like x plus 8 over x squared plus 9, this would converge because it's 1 power larger plus 1 in the denominator. Now I make this x squared plus 8 down here. Now all of a sudden that does not converge, that diverges, because that's assumed to be only one power larger, which is not big enough. That drops you back to the harmonic series, which is no good. It will not converge. So that's how we're going to decide convergence versus divergence, and that's how we kind of dive into the back part of this lesson in 19 through 24. A couple of key points to point out for you, just so you're able to kind of see them. You're not going to deal with any e's or ln's. Remember that a square root is a fractional power. So if I have something like 1 over the square root of x, or square root of n is what the book will be, this diverges. This is less than 1 full power larger in the denominator. That immediately just diverges. Okay, but if I had something like 1 over x to the 3 halves, this is larger than 1 power larger in the denominator. That converges. Now coming into like x powers or powered x's. So if I have something like 3 to the x power, this is powerful enough that this converges. And actually, it's powerful enough even with the x above it that it still converges. That's larger than a harmonic. The 3 to the power of is more powerful than the x. Now, and it'll stay that way over time. The number 2 a power is more powerful than a blank value growth, because this is like a 1, 2, 3, 4 pattern. This is a 3, 9, 27. This is a very rapid growth when you have exponential growth. So that exponential function, that exponential power, is going to grow much faster than the regular x value. Hopefully this is all coming together for you okay. Again, we're on page 618, working problems 1 through 10 and 19 through 24. And just like always, if you have any questions or concerns, feel free to ask me. Have a great day, guys.